Hello everyone, this is the video on Newton's laws, the introduction to Newton's laws. This is what you would have already seen in class on Wednesday, the 28th of November. So if you were already in class, you've already got these notes. But if not, then these are for you. We'll go over these terms during this lesson. Oh, sorry, there's one we actually probably won't cover. I probably won't get to equilibrium, so don't worry about that one so much. But I want to introduce you to all of Newton's three laws and tell you why they matter to us. And the interesting thing about Newton is, this is Newton's first law. I'll tell you a little history about Newton while you're recording this. Newton was a famously smart individual. He was a genius. Perhaps if we had to say if anybody was the characteristic of true genius, we could argue that he is. He not only wrote mathematics, he wrote an entire study of mathematics. Calculus is based upon work that he did. He and many other people, obviously, but he was able to publish this work by the age of 24. He also was instrumental in creating physics as a science. Physics never actually existed before, in a very real sense. It didn't exist before Newton's laws and the study of how Newton's laws interact and how the other researchers before him made these possibilities happen. The important thing about Newton is he gives a lot of credit to people who came before him. He says, if I've seen farther than others, it is because I've stood on the shoulders of giants. So, giving credit back to all the people who came before him, that he used their work to figure out what he knows now. These three laws are some fundamentals he described. This is only the surface of what he's described as far as physics is concerned, but it's important stuff for us to know. To the first law, in Newton's first law, an object at rest stays at rest unless acted upon by an external force, so something other than the object itself. It has to be a force from something interacting with that object. An object in motion continues to travel with a constant speed in a straight line unless acted upon by an outside force. Again, outside force, something other than the object, something interacting with the object. Here's something you might want to think about. Constant speed in a straight line, so constant direction and constant speed. So if you have constant speed and constant direction, you have a constant velocity. That's kind of an interesting thing to bring back from our previous units. So we're saying you have a constant velocity. So an object, the fact that an object wants to continue in motion or wants to stay at rest is known as inertia. Each object has a certain inertia, which is known as a resistance of an object to a change in its state of motion. In other words, going from moving at a constant velocity or from sitting at rest into either moving or stopping. There's a force required to do that. Something must make this object change its state of motion. So for example, let's say we have ourselves in space, and we're going to sit here and we're going to throw a ball in space. As soon as you let go of that ball, if there are no forces of gravity around it, once that ball is let go, it goes forever. It goes until something else acts upon it to stop it or slow it down or change its path or make it go anywhere but in a straight line. If you were to take some keys on the end of a cord right now and spin them around, it's moving in a circle. But the only reason it's moving around in a circle is because there's that cord attached to them. If you were to let go of that cord, it's going to fly off in a straight line in whichever direction it happens to be facing at that time. It's going to want to continue in that straight line path, and then gravity takes over and pulls it to the ground. You can also think about this as far as winter driving is concerned, because hey, we're about to get to that season of driving, the ever so fun time of year when the roads are slick. If you're driving down the road and let's say you're going 50 miles per hour and you get to a patch of ice and you're trying to stop, let's say you try to hit the brakes when you hit this ice and you're going 50 miles per hour. The whole time you're on that ice, you're hitting the brakes, you're sliding, you're probably still going to be going 50 miles per hour until you can hit a part of the road that's got a little more resistance so you can slow down. Alrighty, you can also think about that as far as taking a corner is concerned. Sometimes when I'm driving on the road, I see people who have taken the exit ramps a little too fast, and the icy conditions kind of caught them, and they tend to go off in a straight line off the ramp. You can see that. That's Newton's first law right there. They went off in a straight line path because there was nothing to act upon them to make them go around the curve. So, Newton's laws in action. Inertia is obviously mass, so the resistance of an object to a change in a state of motion is actually going to be measured as mass. So for objects that we study, we're going to assume that its resistance to a change in a state of motion must be its mass. So Obviously, if you tried to push a rather large thing, like let's say I asked you to push a Mack truck, you're probably going to have a lot of trouble moving that thing because the mass is huge. It has a lot of resistance to a change in its state of motion. Whereas if I asked you to go push a smart car, you'd probably have an easy time because they're rather small things. Or if I asked you to pick up a pen and toss it, easy, not a lot of mass. So I've already told you about the idea of while you're driving, you continue in a straight line path. The only reason you'll stop is if you hit the brakes. That's an outside force acting on the wheels to cause the wheels to stop. You also kind of slow down when you're driving because there's air pushing on the car. The air is the reason why you slow down, that air resistance. Also the fact that there's friction inside the mechanics of the car, which will cause it to slow down over time. But otherwise, that car will continue on forever. If we could somehow launch a car into space, it'll fly on forever. It'll just keep going. There'll be nothing to stop it. Alrighty, oops. Sorry, there was a mistake in the order of the slides there. So now it's all fixed up. So we should go on to Newton's second law next, talking about this whole idea. This whole summary is actually saying this. And that just means, you might actually like it better if it was written like this. The asterisk just means multiplied by. So what it's saying is F net equals MA. Well, let's figure out what F net means. So F net is going to mean net force, and that's the net force acting on the object. In other words, of all the forces acting upon it, is there an overall force that's acting on it that's winning, that is doing more than, say, the other forces? It's the overall force acting on it. Like if I said I had $30 and I lost 20, what's my net amount of money? 10. I had 30, I lost 20, I have 10 left over. With forces, imagine that you're pushing on a person. Let's say one person is pushing on another person. One person pushes with 500 towards the person, and the other pushes with 400 against the person. What's your net force? 100 going that way, right? So that's the idea behind net force. M is for mass, A is for acceleration. These are familiar things. Well, mass maybe not. Mass is maybe new. You're used to seeing that as meters. Meters happens to also have a lowercase m, and so does mass. That's unfortunate. When you see it in the formula, keep in mind that that means mass, not meters. The units for these, which are fairly important to know. Sorry, I'm having issues with this board being weird on me. The units for force are newtons, go figure. Newton discovered them. We should probably give credit to him. Kilograms for mass, that is a lowercase k right there. Please make note of that. And acceleration, hopefully you're familiar with that being meters per second squared. We've already seen that one before. Okay, well, there's a big distinction in this country about mass versus weight, actually everywhere, really. The idea of mass and weight is a confusing thing. In our country, we measure things in pounds, and that's actually a weight, which is confusing, because in other countries, the measure thing is kilograms, and that's actually a mass. So it's kind of important to know these differences so we can describe what they mean and how they relate to forces. And for the first part here, we say, well, here's mass. Mass is measured in kilograms. It is the amount of matter in an object. In other words, it's the amount of matter something is made up of. If I said that something has mass, I'm telling you that it's literally made up of this much stuff. There's this much stuff that makes it up. This is a property that cannot change spontaneously unless you lose part of yourself. That would be the problem. I mean, obviously, if you change your mass, you've lost some of the things you're made of. Well, that's not good. So your mass doesn't really change, per se. Maybe over time. As you were younger, you were very small, you weren't made of as much matter. You got older, you were growing, you ate a lot of food, so you could gain all those molecules and those different atoms. And now here you are, you're a larger person. You've gained mass. So mass is what you're made of. A quick example of why that's important. Let's say you're here on Earth, and your mass is, I don't know, let's just say the person we're thinking about is 60 kilograms. Let's say we take them to the moon. If they're on the moon, are they going to have the same mass? Yes. We didn't change how much they had in them. We didn't change how much they were made of, the amount of matter that made them up. Now, would they weigh less? Gravity is weaker on the moon, for sure. Alrighty, volume and density I have up here just so that we're clear on those definitions. I want to make sure that you all know them. Every once in a while I get people who say that mass is the amount of space an object takes up, but that's not right. Volume is the amount of space something takes up. Make sure you're clear on that idea. And then density is mass divided by volume. It's mass per unit space. Now here's weight. That's the big one we're thinking about, because weight is actually a force. It's known as the force of gravity. This is the force of gravity. Now we just learned Newton's second law, which means if this is a force, then, and by the way, it's the force that an object experiences based on gravity pulling on its mass. So if we know that it's a force, then F net must be equal to ma. The force must be equal to mass times acceleration. And we say, okay, cool, then this F must be the force of gravity. Mass can't change. I wouldn't write that down differently. And well, g is the acceleration of gravity. So we're going to say that the acceleration we should have in this equation is g. There we go. So in order to find weight, you would use mass times the acceleration of gravity. And we know that this is 9.8 on Earth. We're going to find our weight on different planets too. That'll be a lot of fun. Keeping in mind, your mass doesn't change if I move you from one planet to the other. Your weight would, though, because the gravity is different on those different planets. Third law. When two bodies interact, and by the way, you can pause this at any point in time, obviously, to record stuff. When two bodies interact, the force of object B on object A is equal to in magnitude and opposite in direction to the force of A acting on B. So therefore, the force of B on A is equal to the force of A on B, except with a negative sign to show that it is opposite. And that's kind of like the idea I showed you before, where imagine two people were pushing on each other. But let's assume that, for example, here I am standing in front of the screen looking really goofy, because here I am teaching and there's nobody really in this room right now. Kind of a bizarre thought. But then again, here you are sitting at your computer listening to somebody talk to you. Who's not really there? Anyways. So here you are. Let's say we're standing on the ground. There's a force of gravity pulling you downwards. We know it, because if I jump, it'll still pull me down. Gravity pulls us downwards. Something must be pushing up on me. This is known as a normal force. I'll say that, or it can also be written as a script N. If the force that I have going downwards is 670 newtons, how much must the force going upwards be? If I'm applying 670 newtons downwards against this floor, and I'm not going through it, then this must be giving me exactly the same amount back. The other example you can think about is, let's say that for some reason you run into something. You're walking through your doorway and boom, you smack your shoulder on the door frame. Oh, goodness. It's not like it hasn't happened to you before. Don't pretend like it hasn't. So, you run into the door frame. Well, if your shoulder applied 100 newtons to the door frame, how much did the door frame apply to you? 100 newtons. And that's why your shoulder hurts. It's not because you hit the door frame. It's because when you hit the door frame, it hit you too. It gave you 100 newtons back. That's what actually hurts. People asked about breaking boards in class, which is something entertaining that we do in martial arts. And one of the things you don't want to happen when you're breaking a board is you're sitting there and you're trying to break this thing. So you slam your fist against it, and if you hit this board, let's say you smack your fist on it, and you apply a force of, let's say, 1,000 newtons, and the board doesn't break, how much has to come back to me? All 1,000 newtons. That's not good. Now, what can be a better trick is when you go to break the board, if the board breaks, the board takes a part of that force, but you're still in motion. So you don't feel this whole 1,000 back to your hand. You feel, I don't know, maybe 400 back. And the rest of that 600 newtons that's left is involved in this board going flying and your hand continuing through. That's the interesting thing about board breaking. So I thought I'd add that as a side thing. But basically, let's focus on the idea of equals and opposites. If I was to put a book on a table, and that book gave a force of 50 newtons to the table downwards because of gravity, what does the table give back? 50 newtons upwards, of course. Alrighty, you see it over here, you got this picture of Newton. And everybody's story on him is that the apple hit his head and he realized, oh my god, there's gravity. Except all through history, small children and adults alike have been noticing that when things fall, there's gravity. That wasn't the big deal. What he noticed was the force of gravity pulling the apple down was the exact same force that was causing the moon to revolve around the Earth. So the force of gravity on the apple was the same force that was keeping the moon going around us, which was therefore the exact same force that caused all objects and planetary bodies to revolve around different things like the sun and the moons around Mars and things like that. It was kind of a big idea. So it wasn't just really the apple, it was the fact that he related the force of gravity of the apple to this giant object of the moon, which was kind of crazy at the time. Alright, so we got this person standing on the Earth, and we're talking about the third law, so it's kind of an important thing here. Which direction does the force of gravity pull? Always to the center of the planet. So the force of gravity of Earth on this person is pointing inwards. What is the equal and opposite force that the Earth feels from the person? Because something has to be equal and opposite here, right? Newton's third law says it has to be true, and it is. The tricky thing is, it's not the surface that they're standing on. That's not actually the reverse force, the equal and opposite force. Because as soon as this person jumps, gravity is still pulling on them. There's something else there. And the interesting thing is, there's a force of gravity that's equal and opposite of the person pulling on the Earth. So how's that work? You got a force of gravity of yourself pulling on the Earth, and you're pulling on the Earth while the Earth is pulling on you? That's bizarre. So why doesn't the Earth move towards you? That's an interesting question, because they're getting equal forces. So if both those forces are equal, and we say I have 670 newtons, let's look at me. So 670 newtons, I'm pulling the Earth towards me with 670 newtons. And that must be equal to ma. So what would the acceleration be? Well, the mass of the Earth is basically this. Goodness. And the mass of me, well, that would be like 72-ish. I think I'm wrong, but don't worry about it. Somewhere in the 70s. So, which one of the two of me is going to, or which one of the two of these is going to accelerate more? If they both experience the same force, which one's going to accelerate more? Obviously, I will. I'm very small in comparison to the Earth. My 670 newtons of force, if you plug this into that equation on the left here, that acceleration is going to be a really dinky number, one that you couldn't even care about. So the Earth is, yes, getting pulled towards all objects on it, but it's so small that you can ignore it. It's actually mathematically insignificant, so you can ignore it completely. So that's an interesting thing. That gets us thinking about some ideas here, like say, how about a rocket? How about like the Apollo rocket? So it's flying through space. And how does it do it? Well, it ejects fuel out the back. So if a certain amount of force is required to send out the fuel, then this force goes back that way. Force of fuel. Well, what force does a rocket have to get? The exact same. Force on a rocket. So what if you sent out a lot of fuel out the back of this? So you have another little piece of fuel, and a little piece of fuel, and another little piece of fuel, little particles getting sent out the back of this thing. All these little things get pushed out the back. Well, all of those forces have to push on the rocket, right? So each of them keeps adding up and adding up until you can actually push this thing forward. It takes a lot of fuel because the masses of these things are so tiny. So if you think about it, if they feel a force, the mass is very small, the acceleration must be big. That's why the fuel goes out of the back of it very fast. The rocket may not go as fast because it's getting the same force, but its mass is much greater, so its acceleration will be less. It'd be like this example. Let's say we have two people pushing on each other. So two people push on each other. This person pushes, oh, actually, let's just say this person on the left pushes on the person on the right. They push with 300 newtons. So what kind of forces do they get back? 300 newtons. Let's say that this person has a mass of 150 kilograms, which is ridiculous, I know, and this person's mass is 100 kilograms. I mean, these are giants. They're giants pushing each other. Why not? So, which one of these two accelerates more? I think you already know, but let's solve it. So F net equals ma. We'll solve it for each one. So they both feel 300. Let's look at the heavy one first. I say heavy one, they're both heavy. Goodness. Times a. Divide both sides by 150. So your acceleration for this one is going to be just 2 meters per second squared. This is obviously the wrong number of sig figs, but please don't worry about that. We're just going to draw into this is to get an idea. For the other one, F net equals ma again, except the net force is 300, and this time the mass is 100 times a divided by 100. A equals 3.00 kilograms. Oh, 3 meters per second squared. Again, I'm not being consistent with my sig figs. But clearly that one accelerates more. 3 versus 2, the lighter person is going to be moved more by the exact same force. That's the same reason why if you walk over to a wall and push on it, you'll fly backwards. It won't. It's got a lot more resistance than you do. A lot more inertia. I want you to think about the idea of a gun and a bullet as we go here. So when you fire a bullet from a gun, goodness, I can't draw. It's supposed to be a gun. Man, I don't even know. Okay, anyway, so it's a gun. So we fire a bullet from it. There's a bullet, goes out that way. The force acting on the bullet, it'll be force acting on the gun. Oops, we don't want to use that because that's FG. Force on the gun. Are they equal? Yes. Equal and opposite. Equal, equal, force on bullet. So the question is, why does the bullet travel so much faster? Think about the mass of the bullet. It's tiny. It's like grams. Tiny. And the gun, well, maybe it's a kilogram. Doesn't matter. That's a lot bigger than the other one. The reason why a gun doesn't accelerate as fast as a bullet is much more massive. It has more inertia. Bullet has a lot less mass, less inertia. It'll have a larger change to its state of motion. If you have any questions, please let me know. Hopefully you enjoyed. Hopefully you have a clear understanding of what's going on. Keeping in mind the idea of Newton's 3 laws. First law about inertia, objects tend to travel in a straight line path or sit at rest unless acted upon by outside forces. Number 2 says that a net force will result in an acceleration, and you can calculate it using F equals ma. F equals mass times acceleration. And lastly, the third law, that for every action there's an equal and opposite reaction. It's the reason why in the movies, and they don't show this, when somebody punches somebody else in the movies, they don't pretend like it hurts their hand. It would, because whatever they supply to the face of the other person is coming back at their hand. So, ask any questions you got. Otherwise, see you in the next video.